And she is live. Yes, little Miss Shaggy Shaggerson here is getting very shaggy again. It's hard to tell which end of the dog is which, but the one white paw is in the front. That's how I remember. Now I'm going to put her down. Down you go. Oh, heavy for such a little thing. Okay, she's comfy. She'll be okay. She's going to pay rapt attention because she loves trigonometry. All right, so yes, that's what we're doing. We're doing trigonometry. Welcome to Math with Doug. I'm wearing Newcastle United. Newcastle is a city in the northeast of England. And this is not the normal colors. This is the only purple sports jersey I own. It's purple. Anyway, let's move on to the math. Okay, so last lesson, we covered the sine formula and the cos formula in trigonometry. We had a lot of review, a lot of angles and stuff, and a lot of Pythagoras, but I'm going to start this week's lesson with a bit of review. Mainly I want to review the sine formula and the cos formula, because I don't want to just launch into the next thing. I want to have a bit of a sine formula, cos formula springboard into the next thing. Okay, so here we see a situation with a right triangle. We know those formulas are very useful for solving a right triangle, and I think the students should realize by now that we can actually use either the sine formula or the cos formula to solve this. I'll write them up here. Sine of angle is equal to the opposite over the hypotenuse, that's a P, or cos of angle is equal to the adjacent over the hypotenuse. So we see this and our minds might immediately leap towards this one, because we can see that the 16-inch side that we know in this right triangle is opposite the 47-degree angle that we know. So we might say, oh, well, it's obvious, we just use this formula. And of course, if we do, it'll look like this. Sine of 47 degrees is equal to 16 over x. I'm doing the trade. X is therefore equal to 16 over sine 47 degrees. The trade, what's that? Yes, I have covered it before, but just in case, when you have your unknown in the denominator, you can do 2 steps of algebra to gradually move things around so that the unknown is isolated on the other side of the equals. Or you can do a shortcut. So all I've done is a shortcut. I did 2 steps in one. So the x moved over here, the sine 47 moved over there. It works algebraically. That's what I call the trade. Okay, so therefore, if we just do 16 divided by the sine of 47 degrees, we're going to have the length of the hypotenuse. So I'll get my calculator and I'll do that. Lots of chalk dust on this thing. 16, I'll make sure I'm in degree mode. Always remember in trigonometry to keep checking frequently that you're in degree mode. Okay, 16 divided by sine of 47 equals 21.87. I'll call it 21.9. And it will be inches because this opposite side that we were working with was measured in inches. So we know the length of the hypotenuse. Now, we could use the cos formula instead, but we have to do an extra step in between. So this is an either or. We don't have to do both of these. So, or I could say, wait, 180 minus 47 minus 90 gives me 43 degrees, does it not? Yes. So therefore, this angle here is 43 degrees. And from the 43-degree angle's point of view, the 16-inch side is adjacent. Therefore, I can use this formula. Cos of 43 degrees is equal to adjacent 16 over hypotenuse x. Again, I find myself doing the trade. X is equal to 16 over cos of 43. And now I simplify 16 divided by cos 43 equals 21.87. That's the exact same number. It's rounding to the same as well, of course. So it's x equals 21.9 inches. Okay, so actually this is just as good a method as that, but we had to do that extra little step first. And then what if we wanted to know this side? Ooh. If we wanted to know this side, we could find it with the math that we already know. We could, for instance, we could do this sine formula, find the hypotenuse, and then because at that point we know the hypotenuse and one of the legs, we could use Pythagoras' theorem. And Pythagoras' theorem would give us the missing side. It works with right triangles. So that would become a two-step process. Or we could choose this method. We could start with the subtraction from 180, get the 43, use the cos formula instead. We still get the hypotenuse, which means we still have the information we need to use Pythagoras' theorem. So we either have 2 steps or 3 steps using all these formulas that we already know in order to find this side here. Wouldn't it be nice, though, if we had another formula that could do that in one step? But we do. Okay, so yes, I am being coy. I'm going to do some erasing. So that was a useful little review. And of course, I could also do the Pythagoras. In fact, I think I will, just for fun. I'm going to do the Pythagoras as well. So the final step from either of these methods I'm going to do over here. We know that Pythagoras is c squared is equal to a squared plus b squared. If a and b are the legs, there's a chair in my way. And c is the hypotenuse. The hypotenuse is the 21.9, so we have 21.9 squared is equal to, and it doesn't matter whether we call this leg a or b, so I can say is equal to 16 squared plus b squared. Therefore, b squared using algebra is equal to 21.9 squared minus 16 squared. I haven't even simplified all this stuff yet. And in fact, I can even go further. B is equal to the square root, because I know I'm going to end up doing that, of all of this 21.9 squared minus 16 squared. Now I'll just get my calculator and I'll finish it off. I want to find out how long that is without using the new formula. And this is all I would have to do, and it's really not very much work. I'm not complaining about, oh, so many steps. These are short, easy steps and fun to do actually also. So I am doing the square root. Where's my square root on this calculator? And then it's helpful to use the bracket keys. So the square root of, open bracket, 21.9 squared minus 16 squared, close bracket, equals 14.95. And that will, of course, be inches. So this is 16 inches. This one's just a little shorter, but we kind of expected that because we have a 47-degree and 43-degree angle. This triangle is almost a right isosceles triangle. So the two legs will end up being close together in size. And that's what happened. So all of this is really cool. It's all fun. And of course, these 2 steps aren't very much work. And these 3 steps that end the same way are also not very much work. But it's still cool to also have a formula that will do it in one step. So I am introducing the 3rd formula now, finally. How much time have I used? I want to do quite a few examples of this new formula. So I'm going to go right back to the beginning of this problem. I'm going to erase this information and pretend I don't know yet that that angle is 43 degrees. I'm erasing this formula. I'm erasing the sine formula. I'm erasing the empty formulas we have up here and the Pythagoras. I'm doing a lot of erasing, and now I'm going to write in the new formula. The new formula is 10 of theta, theta being an unknown angle, is equal to opposite over adjacent. And we are pleased to see it's not very different looking. You can see that the steps in the algebra, the steps in the simplification, are not going to be very different from the previous 2 that we've already gotten used to with a lot of practice. I'm doing something with this laptop right now, which is turning down the volume because it's making noises. So this is going to have very similar looking algebra to when we did the other 2 formulas, but there is still a couple of things that are different. Instead of having opposite over hypotenuse or adjacent over hypotenuse, now we have opposite over adjacent. But fortunately, we've already gotten used to the meanings of those 2 words, those 2 names that we've given to the legs of the right triangle so that we know which leg we're talking about. And then, of course, the 3rd side of the triangle is the hypotenuse, which we've known the name of for a long time. So that's one difference. We're mixing opposite and an adjacent into the math here without a hypotenuse being involved, which is useful because when we look at this problem and we realize we were trying to figure out a way to find this side, well, the hypotenuse does not have to be involved. We have this side, one of the legs. We have this side, the other of the leg. This one we have to involve because we know it. We need to have some information we know. The angle we have to involve. This other leg has to be involved because it's what we're looking for. There's no reason for the hypotenuse to be involved, so this formula is very appropriate. And the other thing that's different, of course, it's the tan button. But I don't think anyone is too alarmed about a new button on the calculator because we have been doing trigonometry for a little while now. And we started using the sine button, which I'm pointing at, but may not be able to focus the camera on very well. The sine button and then the cos button. We've already gotten used to using this, but of course they come as a group of three, sine, cos, and tan. All the students have been noticing that tan button all this time and knowing eventually we were going to use it for something. Well, the way we use it is very, very similar to the way we use the sine and cos buttons. So therefore, this is going to seem like the same math. Just slow down and don't accidentally hit the wrong button, and slow down and don't try and put the hypotenuse in this, and then you should be fine. So let's do this formula right now. Tan of theta, in this case it's tan of the 47-degree angle, has to be equal to the opposite, which is 16, over the adjacent, which is x. So all three of the ways that I've done this so far, I've ended up with that need to do the trade, which doesn't always happen. It depends on what you're looking for in the triangle, whether your x ends up in the denominator or not. But just like with the other two formulas, I can say the same thing. There's three things in the formula, which means there's three different ways of using it. Either the angle is the unknown, or the opposite is the unknown, or the adjacent is the unknown. So there's going to be three different ways of using the formula and three different looks to the algebra that you use to simplify. But they're very similar to the three different ways of using the sine formula and the three different ways of using the cos formula. So I'm going to do the trade. That's what I'm doing next. X is therefore going to be equal to 16 divided by tan of 47 degrees. It's time for me to plug in the tan of 47 degrees. So X is going to be equal to 16 divided by what? Tan 47 equals 1.072. Aha, there's another thing that's slightly different. With the sine and the cos, we got used to the idea that we're always getting values between 0 and 1. But with the tan button, sometimes you get a value that's over 1, 1.072, etc., etc. I'm going to 4 decimal places like I usually do. So it's 16 divided by 1.0724. And I could just use the entire decimal when I actually give the final answer, but as I've been doing in these lessons, I'm just going to write it down to 4 decimal places, and then when I do the calculator, I'm going to clear it, and I'm going to use the 4 decimal place version. So you get a slightly different looking answer if you go to 4 decimal places or forever decimal places. Forever decimal places is more exact, but 4 decimal places is exact enough so that your final answer will round to the same thing as anyone else's final answer if no one made any mistakes. 16 divided by 1.0724, 1.0724 equals 14.9198. I will round that to 14.92 inches. Now I shouldn't have erased everything from before because I can't remember now exactly what I had, but I know it was really close to this. It was 14.95, something like that. So you see that it's extremely close to the value we got using the other methods. The method where we did it with 2 steps with the sine formula followed by Pythagoras, and the method where we did it with the 3 steps with the subtract from 180 followed by the cos formula followed by Pythagoras. We're getting an answer that is so close that if we want to round it to the nearest tenth, it's rounding to the if we want to round it to the nearest unit, it's rounding to 15 inches. That's good. Okay, so it's a new formula. It doesn't work very differently from the others, but we have to do a few examples to get used to it. Let's draw another triangle. Before I erase, I'll draw the new triangle. And of course, I like to do lots of different things. So in this case, we were looking for the adjacent. I want to do one where I'm looking for the opposite as my next example. I'll draw the triangle over here, and what I'll do is I'll make a triangle that's really not anywhere near as close to being isosceles as that last one. Ruler just about doesn't reach. Good enough though. Okay, so there's a right triangle. This time, this angle is going to be quite a lot less than 45, and this one's going to be quite a lot more than 45 degrees. And of course, I can sort of make up angles that look right. I could say, oh, that looks like around 28 or something. But what I can also do is measure with the protractor so that we get an answer that we know matches the drawing quite well. So I can give either of these. I think I'll measure this one. And that looks like about 64 degrees. And I can also measure the side length, again, to make it match the drawing well, instead of just making up some random number. And in this case, I knew the opposite, and I looked for the adjacent. In my next example, I want to know the adjacent. So measuring this, that is, I will call that 11 inches. 11 inches. Therefore, there's my x. I'm looking for the opposite this time. Let's use the formula. We will erase this example. And I'll erase all of this except the formula itself, the empty, unfilled-in version of the formula. We want to keep that there. So, filling in the formula, tan of 64 degrees is equal to the opposite, which is the x, over the adjacent, which is the 11. And then the algebra does not have the variable in the denominator. I'm not doing the trade. X is going to be equal to 11 times tan 64. So I like writing the x on the left, so I decided to do that. But if I am going to get rid of this 11 away from this x with algebra, I multiply both sides by 11. Shortcut, I just multiply the other side by 11. So it's the tan 64 that's getting multiplied by 11, and that's what I'm doing. Okay, 11 times tan 64 is going to be equal to, going to 4 decimal places, as is my habit. Again, making sure I'm in degree mode. You can press a button by accident and go into the wrong mode, so I like to check quite often. Tan of 64 equals 2.0, this one went over 2. 2.0503. Okay, let's experiment with this. Do I clear and actually do 11 times 2.0503, or do I just do 11 times this whole decimal that's sitting there in the calculator? Let's do it both ways. If I keep the whole decimal in the calculator, I just have to do times 11 right now. Times 11 equals 22.5533 inches. But if I do 11 times 2.0503 instead, 11 times 2.0503 equals 22.5533. This time it ends up inches, put the unit of measure inches. This time it ends up being the same when rounded to 4 decimal places. But this one in the display, it's saying 22.5533, and it stops there. It stops after that 3. But the one where I use the whole value of tan of 64, I'll do it over again. 11 times tan 64 equals. It doesn't stop. It's 22.55334226. So even though they rounded to the same thing when rounded to the nearest 10,000th, this was already rounded to the nearest 10,000th because I had only gone to 4 decimal places here. And this other one went past that, and I had to round it up to the nearest 10,000. I just happened to get the same value. Sometimes the value will be slightly different, but it's not going to be different enough to cause a problem when you're trying to solve a problem. And that is the point. Okay, so now we've tried this new formula to find the adjacent, and then we've also used it to find the opposite. Let's use it the third and last way we can use this formula, which is to find the angle. That'll be fun. Okay, I'll erase the answer. I'll keep the formula. Erase the triangle. Now this time, I'll draw the triangle over here. So I'm sort of randomly choosing lengths of sides. I do want the two sides to be perpendicular to each other, which I did by eye, but I did it quite well. Now I'm just going to measure them. And of course you can do this with triangles that are drawn to scale. You can sort of make up values if you want, and you'll get the calculations will work. But again, I like it when the calculations and the values I get match the drawing quite well. So I'm trying to use some of the real values when I can. So this is 14 inches in length. And I haven't drawn my hypotenuse yet, but I'll draw it soon. This side is 21 inches in length. And now, is this long enough? It's not quite long enough to draw the hypotenuse, but I'll just draw most of it and then move this a bit. Finish that. There. Okay, so we have a triangle. And one of the cool things about this tan formula is I haven't even decided yet which angle I need to find, and it actually doesn't matter because either of them involve using this formula. So I can call this theta the way I normally like to refer to an unknown angle, but if I'm going to give this a variable, I don't want to use the same one. So I'm going to call this one angle alpha. Okay, alpha's kind of crooked, but it'll be good enough. Okay, so I'm actually going to answer this twice now. So tan of theta, I'll do the theta first, is equal to the opposite, which is the 21. Again, remember, put your finger on the angle that you're using when you're doing a problem, if you have trouble remembering and orienting yourself. But I think this is temporary, that students like to put their finger on the angle. From here, I can see that the opposite is the 21. And the adjacent is the 14. So I can solve this now. I can simplify right away. 21 divided by 14. It's going to give me 1.5, isn't it? 21 divided by 14. Yes, that is 1.5. So tan of my unknown angle is equal to 1.5. And if I really wanted to write it to 4 decimal places, I could put 3 more zeros if I want. But now I'm doing the inverse tan. Inverse tan of 1.5 is going to give me the angle. So I'm doing second in this calculator. It's a little second button, and sometimes it's shift. Second tan of 1.5 equals 56.3099. And the next number after is a 3. And that, of course, is an angle, so it's degrees. Now I'll do it again. And I'm just going to keep it to 4 decimal places. And it's reasonable. 56 degrees looks good with my drawing. Now if I do it again, tan of alpha. Well, we could figure out what alpha is without this formula, couldn't we? We know that alpha would be 180 minus 90 minus 56.3099. So it's going to be around 34, a little less than 34 degrees. We can see that coming. But let's find it using the formula. Tan of alpha is going to be equal to opposite, which is the 14, over adjacent, which is the 21. There I am putting my finger on the angle. This time I'm using this angle. So the 14 has become the opposite instead of being the adjacent. Therefore, tan of alpha is equal to 14 divided by 21. It's going to give me 0.66667 rounded to 4 decimal places. Therefore, inverse tan of 0.6667 is going to, I can kind of predict what it's going to give me, but I'll do it anyway. Inverse tan 0.6667 equals 33.6914. 33.6914. 0.6914 degrees. That is rounded to the nearest 10,000th, to the nearest, rounded to 4 decimal places. And of course, we realize that if we add this and 90, we should get 180, or we'll get a decimal that's extremely close to 180. So I'm going to do it. I'll start here, 56.3099 plus 33.6914 plus 90 equals 180.0013. 180.0013. So 180 degrees. Interesting. The only tiny little difference between 180 and this number happened because of the rounding that I had to do along the way. And it shows us reasons why we should have a lot of confidence in this formula. What am I doing for time? It's pretty good. I've used the formula 4 times, I think. I can't even remember now. I managed to use it twice just with this triangle. That's kind of cool. But we need some more practice. So we've used the formula twice to find unknown angles, and we've used it to find an opposite, and we've used it to find an adjacent. So let's find another opposite and another adjacent. Let's have fun with this. So I'm going to erase. I'll draw 2 right triangles without trying to measure anything. I won't try to measure angles or side lengths. Just draw 2 different right triangles, and then I'll figure out the values we want to supply in the question with measurement tools, including the protractor this time. So here I'll put, let's say I'll make this 20 inches. And now I'm going to just randomly draw a side length. I'll make it kind of skinny there. Quite skinny. And now I'll draw another hypotenuse. I'm not trying to measure this second or third side because I know I can use trigonometry to find them. There. And because I don't want to try to find the angle, so I want to supply an angle. So I'm going to measure to get an angle. And I'll measure this little skinny one. That looks like about 18 degrees. It's hard to write that in here, so I'll do it like this. Okay, and we want to find this. So we're looking for the opposite with that triangle. Let's do another triangle over this way. I'll make this one a little bigger. This time I'll measure this little shorter side, and it is 8.5 inches. Let's draw the hypotenuse. Okay, so in this case, over here I'm looking for the opposite. So here I want to look for the adjacent. So, therefore, this is my x, that's adjacent to this. So this angle, wait, here, I'm looking for the opposite. I know the adjacent. Here, I'm looking for the adjacent. I know the opposite, yes. So this is the angle that I want to measure, and again, I'm measuring the skinny angle that just sort of happened by itself. 23 degrees. Okay, so let's use the formula 2 more times. More chalk, please. I think I need a sip of my fizzy water. Root beer flavored fizzy water. Oh, feels so good to hydrate. Okay, so I'll start with this one. We are using the tan formula to find this side x. Tan of 18 degrees is going to be equal to the opposite, which is the x, over the adjacent, which is the 20. That means x is going to be equal to 20 times tan of 18. X is equal to 20 times 10, checking that I'm in deg mode, 10 of 18 equals 0.3249, and it goes on, but the next number after that 9 is a 1, so 0.3249. So there's a tan value that's not over 1 or over 2. 0.3249, 0.3249. With the tan button, we get more variety in the values that we get. And I'm multiplying that by 20. 20 times 0.3249 equals 6.498 inches. And that is a reasonable answer, isn't it? When you see this triangle, that side is 20 inches, this is 6.498 inches, very close to 6.5 inches. Makes sense. And, okay, let's see how good my drawing and measuring skills are. This one I measured as 20, and that's a pretty good measurement. This should be very close to 6.5, or else my drawing's just not very good. Yeah, well, it's over 6.3, so I'm kind of proud enough of that. Let's do this one. We are looking for the adjacent side this time. 10 of 23 degrees is equal to the adjacent, which is my x. No, is equal to the opposite, which is not my x. It's the opposite, which is my 8.5, over the adjacent, which is my x. This is one where I have to do the trade. Okay, so therefore x is equal to 8.5 divided by 10 of 23 degrees. X is equal to 8.5 over 10 of 23 degrees. 10, 23 equals 0.4245. Okay, clear. 8.5 divided by 0.4245 equals 20.02355. I will say 20.02 inches. Now this one, I had actually measured that as 20 inches. But this one, I drew that side without trying to measure it. So I may as well measure it. 20, is it very close to 20 inches? Yes, it is. Okay. It's a useful formula. When you think about the combination of the sine formula, the cos formula, and now the tan formula, it pretty much covers everything. What happens is sort of an embarrassment of riches, where you're given a situation to solve that involves some triangles, and you look at the information you have to try to figure out which formula you need to find something that is in the solution. And it's amazing how often you realize you have more than one choice. So these formulas are so powerful. Sine formula, cos formula, tan formula, along with Pythagoras' theorem that comes in handy quite often while we're doing this, that information that the three internal angles of a triangle always add up to 180 degrees comes in handy very often while we're doing trigonometry. And in a 30, 60, 90 right triangle, the hypotenuse is always exactly double the length of the shortest side. That one comes in handy sometimes. Don't forget it, because there will be the odd time where you'll have all these formulas and you realize, wait, I just don't know what to do. I don't have enough information. And then if you apply that little fact, then you realize, oh yes, I do have enough information. So it's a toolbox full of extremely useful tools which are useful for right triangles. Trigonometry can handle all sorts of triangles, but we have to start with the right triangles and see how much power we have to solve them. Let's see if I can put together, how am I doing for time? I'm doing okay. Let's see if I can put together a multiple step problem where I have to use the tan formula more than once. That's my challenge right now that I am putting myself on the spot to do. So, multiple step problem where I have to use the tan formula more than once. Let's see what I can put together. I'll start by drawing a side of a triangle over here, and I'm not going to try to measure anything. That might not be perfectly horizontal, but it's pretty good. Okay, and then I'm drawing a right angle So I can finish this and I have a right triangle. Then, let's see. How about if I draw another triangle like this? That shares a side with this one. No, it doesn't, because this is going longer. That's interesting. Okay, here's another right triangle. Now, from this top triangle's point of view, this side has to be either the adjacent or the opposite. It's not the hypotenuse. And what if I say, okay, I know this is 2, and I won't write the unit of measure, but just let's say we know that's 2 inches. Or no, even, you know what? I'm going to say it's 2 meters. Yeah, 2 meters. 2 meters. That's too small. I'm starting over. Just keep this a little bit neater. Okay, so 2 meters. It's hard to label some of these sometimes. And I want to know this angle. I'm not even going to measure it. I'm going to look by eye and say that looks like more than 45. I'm going to call it 52 degrees. Writing kind of small. Okay, 52 degrees. So, and this is 6 meters. Okay, so I'm not measuring very much stuff here. I'm just kind of come up with things that are consistent. If that's 6, then it's believable that little piece is 2. So therefore, using this tan formula, I would be able to find this side. And then, if that's 6 meters, let me actually measure. It looks pretty close to 6 inches. So, I'll say this is 17 meters. And I want to know theta. Did I mess this up? Or did I meet my challenge, which was to come up with a problem where the unknown is this. I need to find this. But this is in this lower right triangle. It's lower right triangle. We know there's a 90. We know we have to deal with theta. That's the angle that we're finding. And we know that the side adjacent is 17 meters, but we don't know the hypotenuse. We don't know any of the angles other than the 90. And we don't know the side opposite this angle theta. But in the upper triangle, we have the 52 degree angle. We know the side adjacent to that, and we could use the opposite side. It's kind of cool. We have a 3-step problem where 2 of the steps are going to be this formula, I think. So if I realize I'm wrong along the way, I'll be embarrassed, but c'est la vie. Okay, so let's do the first step. Tan of 52 degrees is going to be equal to the opposite. That's a very messy equal sign. The opposite, which is my x, over the adjacent, which is my 6. Therefore, x is equal to 6 tan 52. Which is equal to 6 times, what is the tan of 52 degrees? Where's my calculator? Degree mode, yes. Too much chalk dust. Tan of 52 equals 1.2799. Now, I can just use 6 times 1.2799, but this actually brings, when we get into the multiple step problems, it brings up a point I like to make with students, which is that the memory in calculators when you're doing trigonometry can be extremely helpful. Memory meaning that it just already has a value in it. And it just so turns out that I need that value in my next step. So instead of just going to 4 decimal places, I'm writing it down to 4 decimal places because that's very well organized. I like to do that. But I'm not going to multiply 6 by this value. I'm going to multiply 6 by this really long unrounded version of tan 52 that's still sitting in my calculator. So all I have to do is say times 6 equals. And the answer is 7.6796. And that's going to be meters, because we're doing all of these values with meters. So in a multiple step problem, if you keep on rounding off along the way, you introduce a little bit of error each time. And most of us would prefer not to introduce any error at all. But if you do have to introduce error, if you're in a predicament where you realize, oh, I can't really use the memory of the calculator, I need to clear it to do my next step, this trick of going to 4 decimal places is going to make sure your answers are still quite accurate. So we have figured out that this is 7.6796 meters, but my next step, I'll call that step 1. My next step is a really quick and easy step, which is that length, and it really doesn't match the drawing. I really made up numbers this time, so don't expect it to match the drawing. That length is the whole length of that side opposite the 52, but I don't need that in this triangle. I need to subtract 2 from it. So step 2 is 7.6796 minus 2 is equal to 5.6796 meters. And then you can see what's going wrong with this drawing. That I drew it so that this side looks so much longer than that side, but actually it's 7.6796 isn't very much longer. So the drawing's not very good, but that's going to happen. And what I always explain to students is, us math teachers will make sure that the drawings in trigonometry are crooked on purpose, because we want the student to be able to trust the formulas and not try to pull out rulers and protractors and solve everything with that, which can be tempting at times, but trust the formulas. We've developed these formulas for a reason, because they can be trusted. Okay, so now this side here is 5.6796. I'll write it in. But that's only up to this point. It doesn't include the little 2-meter bit, which we don't care about anymore, because now we're able to move down into this triangle. I'm ready for my step 3. For step 3, I want to find my measure of angle theta. Tan of theta is equal to the opposite, which is the 5.6796, over the adjacent, which is the 17. So therefore, tan of theta is equal to the answer I get when I divide there. Oh, the 7.67, that thing still hasn't been rounded, and I can just do minus 2 equals to reproduce this. Now I have 5.67, but it's still not rounded. I still have managed not to round anything while doing all of the steps of this problem. And I'm going to take that value and divide it by 17. 0.3341. Then the inverse tan is going to give me, that fits good. It's going to give me the angle of theta, and I'll have the answer to my question. Again, I can get used to using the memory in here, and this calculator I'm able to say second tan, and then I'm able to put in previous answer. So the 0.3341, but without being rounded, is in there. Previous answer equals 18.4743. Degrees, because it is an angle. Now, we're not expecting me to walk up and to measure this and find out that it's 18.4743 degrees. I can tell by eye that it's going to be bigger than that, but that's happening because of me making up numbers sort of randomly that didn't match the drawing very well. This process still worked. And you can see how you can do a multiple step trigonometry problem that involves using this formula more than once, where you're put into a position where you really need to use this formula more than once. And it's fun. It's a good formula to use. Looking at how much time I have left. I think the next thing for me to do is to give myself another challenge, because towards the end of the last lesson, I had multiple step problems where we used the sine formula and the cos formula. But now that we've introduced the tan formula, how about coming up with a multiple step problem where I have to use all 3? I know I can do it. I'm going to try to make my drawing a little better this time though. So I can erase everything. I'll still leave the formula up there because that's the new thing we introduced. It's good for the students to always be able to see it as we go through the lesson. Let's see now. I'll do the drawing over on this side. When you're using all all three formulas, you don't really know which one you're going to use first, which actually means that the situation is quite flexible. I'm going to measure with inches again though. I'll say there, that's 15 inches. Make sure it shows on the video, it does. And now I'm going to turn that into part of a right triangle. Draw hypotenuse. Got a little bit of extra chalk line there, I'll erase that. Okay, so there, I have a 15-inch side, and I haven't really measured anything else, but I know it's in a right triangle. But now we can do it, I'm doing it in steps, right? We're going to start with, we'll start with this triangle, but we'll solve it to find something that's also in the next triangle. So this side, I'm going to make this side be shared. So I'll make a skinnier right triangle, like this. And how about if I draw this hypotenuse of the middle triangle can be a non-hypotenuse in this one. I'm going to erase some of this stuff so that we can see our little squares that represent the right angles a little better. Okay, now let's see if I can put values and x's in place that put me in a position where I will use all three of the formulas, one after the other. Right now, though, I haven't decided which one I want to use first, because I can do this so that you have to use the tan formula first, or the sine, or the cosine. I can do them in any order, which means there's all sorts of problems like this I can make up that would all be a little different. But that would share in common this idea. That doesn't look like a vertex, does it? But it's a vertex. We're just going to have to blame the chalkboard for occasional imperfections in the drawing. So let's say I decide that I want to know what this angle is, and I'm going to use the sine formula first. I want to avoid painting myself into a corner here. But I want this to be my unknown. I'm not going to put an x on it because it's not the value I'm looking for as the final answer to the question. I am going to put the hypotenuse in. So we're going to end up using the sine formula to find this side. And that is 22 inches. Okay, so we're now in a position where we can use the sine formula to find this angle. Does that make sense? Doesn't really make much sense. That didn't work. Let's see. No, I'm going to erase the 22 inches. And I'm going to measure this angle. And we're going to start with the tan formula after all. So that is a 40-degree angle. Okay, so we will use the tan formula to find this side, which means then we're jumping into the middle triangle, and I want to jump over to that one. So I'm going to say I need to know this angle, and that is 30. You know what? I'm going to measure it again because that badly drawn part, and note that is not 30, it is 31 degrees. 31 degrees. So I'll be able to figure out that one with my first formula. And then using it, it's being adjacent to this 31-degree angle, I'd be able to find the hypotenuse with the cos formula. So I'm starting with the tan formula, then I'm going to do the cos formula. I won't even write them. Which means for the last one, I want to use the sine formula. So this is my x, the hypotenuse in the bottom right triangle, and that means I need to know this angle. (58 degrees). Okay, I have created a multiple step problem that is going to make us do all three formulas. The sine one's going to be kind of low. I'll manage. I'll pull over my chair if I have to. Okay, so what are we going to do to get this to figure out x? We cannot figure out x from this lowest triangle that it's part of because we don't have enough information. We have the 90, we have the 58, we could figure out the other angle, but we need a side. So the side we're going to need is going to be this one, which happens to be the hypotenuse in the middle one. So what we're going to do is we're going to start with tan formula and find this side here. I guess I'll call it A, and then I'll call this, I don't want to call it B. I'll call it H. No, I don't want to call it H either. H means too many things in geometry. I'm going to call it C. C for hypotenuse, but it's the hypotenuse of the middle triangle. It's not the hypotenuse of the bottom triangle. It gets confusing labeling these things. Let's just get into it and answer the question. Tan of 40 is going to be equal to the opposite, which is the 15, over the adjacent, which is the A. Aha. So A is going to be equal to 15 divided by tan 40, which is 15 divided by, what is the tan of 40? Tan 40 equals 0.8391. 15 divided by 0.8391. Not using memory, just using the 4 decimal places this time. 17.8763. And that is going to be inches, but we don't really need the unit of measure yet because we're not at our final answer. Now we're switching into this middle triangle. Cos, I'll do it over here and leave more room. Cos of 31 degrees is going to be equal to the adjacent side, which is the A, which is the one we just found out. That's the 17.8763 over the hypotenuse, which is the side C. We called it C. So I am doing the trade. C is equal to 17 point... I did the trade in both of these steps. 17.8763 divided by cos of 31, which is equal to cos of 31, running out of chalk here. Cos of 31, still in deg mode, cos 31 equals 0.8572. .8763 divided by 0.8572 equals 20.8543 inches. Again, we don't really need the unit of measure yet because it's not our final step. So that means I'm going to just erase this and I'll draw it a little higher. I made some room with this little creative arrow. So that's step 1. There's step 2. So step 3 is going to be the sine formula, the only one that I haven't used yet, but I'm not using it because I want to use it. I'm using it because I need to in this situation. Sine of 58 degrees is equal to the opposite, which is that 20.8543. That thing that we called C before, that's opposite the 58 degrees. 20.8543 over the hypotenuse, which is the x that I was always looking for. Oh, I'm doing the trade in all 3 of these. I didn't really intend that, but it's okay. X is equal to 20.8543 divided by sine 58 degrees, which is equal to 20.8543 divided by, what, the sine of 58, deg mode, yep, sine 58 equals 0.8480. 20.8543 divided by 0.8480, 0.848 equals 24.5923. Yes, and it will be inches. Do do I dare try to measure it. 24.5. Nope. Drawing not good enough for that to match beautifully. But we used all three formulas step by step. And as we've seen, as we've talked about, there are ways we could have just sort of found more information, especially by subtracting from 180. We could have done that in any of the three triangles, which means we would have a 50-degree angle over here, a 59-degree, 50, and this one, a 59-degree angle here, and a 32? Yes, a 32-degree angle there. If we were to just subtract from 180 all three times and fill in the three missing angles, then we would have all sorts of choices as to which formula we want to use for which step. And we would have eventually been able to find anything. And in fact, we can continue and find everything. And that's another thing that's interesting to point out to students. I'm nearly out of time. That in trigonometry, multiple step problems where you have these diagrams with lots of triangles, it can be a little intimidating. But what I always discovered when I was a student was if I looked at the situation and I wasn't really sure how I could get the answer, I would temporarily stop worrying about the answer, and I would just start finding anything I could find. So that subtracting from 180 is really the easiest, fastest way to start doing that. You start subtracting from 180 and putting in extra angles, and then as soon as you realize, hey, I have enough information to use the sine formula to find this hypotenuse, even if it's something like this one, right, you know you don't need, go ahead and find it. It doesn't take long. And you gradually start filling in all of the angles and all of the side lengths. And eventually you realize, hey, that answer that I didn't think I'd be able to find earlier, I could see that's really going to be easy to find now because you keep on giving yourself more information. And the extra information just gives you more choices for what math steps you can do to answer the question. So with that, I think I am going to bring this lesson to a close because little Miss Shaggy Shagerson over there knows that it's nearly over. I don't know how she knows. She knows that it's almost supper time. She's doing her stretch like the Sphinx and trying to look cute because she wants me to feel compelled to feed her, I guess. But it works. It works every day, so you can't really argue with her success. And her tail is just going like crazy. Okay, up you go. Say goodbye to all the trigonometry students. All of us are a little bit smarter than we were an hour ago, including you, right? Sometimes it's the silent ones who are the smartest person in the room right now. Is that it? Right? Okay, so as usual, it has been fun. Thank you very much for being here, and I will see you next time. We have some more trig to follow in the next lesson.